For the first question, we need to fill in the blank. If only a few, all, or most chaotic systems have fractal state space structure, and the answer to this is most. While having fractal state space structure, or having an attractor with fractal dimension, is often a signature of a chaotic system, it is not the case that all chaotic systems have fractal dimension.
Questions 2 and 3 really go together. Some people define fractals as self-similar objects. Others define fractals as objects which have non-integer fractal dimension, in particular non-integer Hausdorff dimension. The problem is that depending on which of these definitions is prescribed to, the other definition can sometimes be wrong. That is, there are objects that are self-similar but do not have a non-integer Hausdorff dimension, and there's objects with non-integer Hausdorff dimensions that are not self-similar. For the purposes of this course, we will consider fractals to be objects that have non-integer fractal dimension, in particular non-integer Hausdorff dimension. For the purposes of this quiz, both of these are true. It is important, however, to keep in mind that when some people say fractals, they mean self-similar, and when other people say fractals, they mean that the object has a non-integer Hausdorff dimension. While the vast majority of the time, self-similar objects also have non-integer fractal dimension, and vice versa, there are pathological examples that contradict one way or the other, and this is something to keep in mind.
Question 4 asks if the fractal dimension of the middle fifth removed Cantor set is smaller than that of the middle third removed Cantor set. Since there's both Cantor sets, we know that they'll have a dimension between 0 and 1. That is, they'll be somewhere between a point and a line. To figure out which will have a smaller fractal dimension, we need to think about which will be closer to a point than a line. With the middle third removed Cantor set, we're removing more mass of the line than in the middle fifth removed Cantor set. So the middle third removed Cantor set will have smaller fractal dimension because it'll be more similar to a point than to a line, and the middle fifth removed Cantor set will have a larger fractal dimension than the middle third removed Cantor set because the middle fifth removed Cantor set has less mass removed and will thus be closer to a line. Since the middle fifth removed Cantor set will have a larger fractal dimension than the middle third Cantor set, this question is false. For this question, we simply need to remember that log of a to the b is equal to b times log of a. Using this identity, we see that log of 2 to the 3 is equal to 3 times log of 2. Question 6 asks us to calculate the capacity dimension of the middle third removed Cantor set. This is actually done step by step in lecture, but I recommend if you've never done this to do this by hand without using the lecture, and come back to the lecture if you get stuck. It's actually a really good mental exercise. As we saw in lecture, the capacity dimension of the middle third removed Cantor set is 0.6309. For the final question, what is the capacity dimension of the middle fifth removed Cantor set? While this procedure is very similar to calculating the middle third removed Cantor set, let's go through it step by step. For simplicity, let's assume this line is 1 long. So in the k equals 0 step, we can cover this line with one ball of size epsilon equal to 1. In the k equals 1 step, we remove 1/5 of this line. That means that the remaining pieces are 2/5 along, and we have 2 of them. So in the case of k equals 1, we need n epsilon equals 2, and epsilon equals 2/5. In the k equals 2 step, we remove 1/5 of something 2/5 long. That means the pieces left are 2/5 of 2/5, or 2/5 squared. And we've doubled because we cut every single one into 2 pieces. Similarly, in the k equals 3 step, the remaining pieces are now 2/5 of 2/5 squared, or 2/5 cubed. And we need twice as many of these. So now we have 2 times 2 squared, or 2 cubed. If you continue in this manner, you'll see the general pattern that you need n epsilon to be 2 to the k, and epsilon to be 2/5 to the k. If we then plug this into the capacity dimension calculation, we see that the capacity dimension, using the same limit trick as it was used in lecture, you get log of 2 over log of 5/2, which equals 0.7565, and that is the capacity dimension of the middle fifth removed Cantor set. And as you just saw, the capacity dimension of the middle fifth removed Cantor set is 0.7565.